Hello, everyone. Thank you all for coming to our second MSET Cuttlefish Speaker Series event of the year. Today, we're proud to welcome Mr. Ankur Agarwal as our speaker. He is a computer vision and deep learning engineer at Plus AI, where he leads the lane keeping effort. And previously, he worked with autonomous robots at Qualcomm Research and NVIDIA. He will give a brief presentation and overview of computer vision and deep learning, and we'll go over some past robotics-related projects that he's been a part of.
All right, thanks, Aaron. So hey, everybody, welcome. I don't even want to call it a talk, actually. This discussion is titled Computer Vision and Deep Learning. So while I was writing this, creating this presentation, I realized there could be a huge mismatch between what you guys expect and what I know. So I thought of making it an overview of perception in robotics, stuff that I've done over time and current state of the art that exists in the industry. So here's what we're going to talk about today. All right, sorry, before that, can you guys hear me clearly?
Yes.
Okay.
Yeah.
All right, awesome. So this year's motivation. So I'm going to talk a little bit about what you guys should expect from this, a little bit about me, and then we're going to discuss some autonomous robots. What does perception mean in the field of autonomous robots? What are computer vision and deep learning in terms of perception for autonomous robots? And then pro tips for approaching a robotics problem, approaching a perception problem, and then we can end with some questions. Here we go. All right, so motivations and expectations. This is not a deep dive. It's an overview of autonomous robots and perception state of the art. So my main goal is to give you an appreciation of the perception problem in robotics and to get you guys excited about STEM and robotics. There's so many cool things to do. And there's more and more use cases as we go into the world. And I would love for it to be a discussion. This is not a talk. So stop at any time or stop me at any time, ask questions. I'll keep an eye out on the chat. And also I think Aaron's going to help me out with any questions if there are.
Yeah.
All right, cool. And if there is any interest, I can always come back for a deep dive in specific subjects or problems. Like I work a lot with all of the fields that I'm going to talk about today. So my apologies if this sounds really simple, because I just wanted it to be like a blanket conversation. All right, with that said, a little bit about me. That top one here is a link to my LinkedIn profile. You guys can check it out later on. So I got my master's in electrical engineering, which was a mixture of image processing and computer vision from USC in 2013. I've been working with software and sensors for perception in autonomous applications since 2011. I've mostly worked with cameras, depth sensors, LiDARs, and radars. These are types of sensors that robots and cars and almost everything that is autonomous in today's world use. So I've primarily worked with software. I am not much of a hardware engineer. At Qualcomm Research, I used to be an engineer. I used to work with quadcopters and warehouse robots. At NVIDIA, I was a senior software engineer in the perception field. I worked on indoor and off-road robots. I'll share some pictures in the next slides. And at Plus AI, where I'm currently at, I'm a senior systems engineer for perception. I do computer vision and deep learning. These are my largest robots yet. So these are Class A trucks, 18-wheelers that pull more than 40,000 pounds of stuff. So Qualcomm Robotics, I'm gonna just dive into these videos. So at Qualcomm Robotics, we used to do small robots that can be programmed to behave autonomously. So I'm gonna click on this link. I hope everyone can see these videos. So these drones that you see, these are the ones that we made. The hardware, the chips that go on them, the cameras like this one, all of this is like our design. And yeah, you're gonna see a cool video where these things fly around. So these robots actually have one Snapdragon controller that we called. So this had a bunch of cameras. These cameras were used to detect objects, to figure out where this quadcopter is. It does not fly off into objects. It can follow a particular trajectory. These drones can also chase each other. So as the first one's flying, the other ones follow it. And this is all done on the device. So there's no external computer or no one else manually controlling these. These are just autonomous flying quadcopters. So as you can imagine, this is a pretty significant challenge because you have these flying machines which fly at a really fast speed. And you have to avoid these obstacles. You have to follow a trajectory. On the top, you'll occasionally see this one quadcopter, which is like this sort of leader quadcopter. It has a 360-degree camera mounted on top of it. And we sitting in one of our back offices can like look at what this drone is seeing. Yeah, that's us. So this is the person wearing one of these VR headsets, and then we are seeing what this quadcopter is seeing from the top. But the other drones, all the other drones are just flying autonomously. All right, that's that. So that's what we were doing at Qualcomm Research. We were trying to come up with compute and processing that could enable autonomy for these small robots. And as you can imagine, this is a combination of hardware and software. So I'm going to go into a little bit of the software that I worked on. This first link here, this is all running on, oops, let's go. Yeah, this is this algorithm called visual inertial odometry. Essentially, with just a phone, we are able to track where a person is going. And they're able to move this phone really fast. But we have a very good estimate of where this person is going. So you can imagine if you put this on a robot, you'll have a very good idea of where the robot is going and how it is going. So right now, this person is holding a phone, walking downstairs. This person is running in office hallways. Yep, that's me on a skateboard. So this is an example of using computer vision to locate an object. And I'll come into why this is useful in future slides, but this is just a taste of stuff that we were doing at Qualcomm. And then similarly, you can just get on a bike. And here is another example of a quadcopter doing something similar. So this quadcopter, as this is flying around, this is in pilot assist mode right now, so someone is manually flying it. But as it is flying, whoops, yeah, it's creating a map of the stuff that it is seeing around it. So that is how it recognizes that, oh, you know what, I should not be hitting this thing, it's an obstacle. Or this is a free space and I can fly into this free space. So this arch over here that you can see on the right side, that's a free space, and all of this area is a free space, and the robot can navigate from one point to another point without hitting any obstacles.
So I have a question. Does it only use, I guess, camera vision or computer vision to get like a model of its environment, or are there other sensors involved?
So there's a good question. There's a camera, and we use IMU. It's an inertial measurement unit. But we can do this with just the camera. The IMU is only a smoother of sorts.
Also, another question for the quadcopter, or like the previous quadcopter, did it use like, or in order to like get motion profile or accurate motion profiling with a camera, does it have to have like object detection, or how does it like track its position with only cameras?
So the tracking of the position with cameras, the previous video that I showed where there were a bunch of points on the image and a person was running with the phone, that's how we detect objects in space. So in computer vision, there's this thing called features. So you look at an image, and everything that exists in an image, it can be assumed to be something that you don't want to hit, right? It's an obstacle. Because if it did not exist, the camera would not be seeing it. So if something exists in an image, it's an obstacle, and then you track points on this obstacle over multiple frames. So you build this model of free space versus occupied space. And you can add obstacle or object detection on top of that, but that's not strictly required. So in this video right now, let's run this again. Each of these boxes that has been created, right? These small voxels, they correspond to an occupied object. And this is not running with object detection. This is an occupied volume in 3D space, and we do this with the stereo depth. So we use 2 cameras and then figure out what is an estimated depth for these for this voxel. Does that answer your question, sort of?
Yeah.
Okay, awesome. So before I go, how many of you are actually, let me just open that screen. How many of you are aware of computer vision and deep learning? I was gonna go into that in the next slides, but since you asked a question like that.
So yeah, like at our robotics team, we use computer vision for mostly just for object detection. I think we've rarely used it for motion profiling. So that's kind of why I was interested in. Yeah.
I see. Okay, cool. So this link, you guys can explore that later, but this is essentially what we built at Qualcomm. Yeah, so this is the processing unit that's essentially the brain of the robot. And then this is that quadcopter. So there's a camera here, there's a camera on the bottom. And we also had we had this insane robotics team which designed some really awesome robots. So there's different designs of different robots, but the brain is essentially the same. It's the same chip inside all of these, but different positions for cameras and different I guess, sizes and models. Right, and I think there's this. Oh, you guys can check out these links on your own time. This is just what we showed at CES. It's similar to what the videos that I share right now. So Qualcomm Robotics for me was mostly working with these small robots and designing our own compute. And there's not a whole lot of, as you can imagine, it's a quadcopter, so you can't put a lot of sensors. And cameras that way are really small and really low power sensors, so which was the best use case for these. Now at NVIDIA, I worked with slightly larger robots, which were this one. This is a robot from Aeon Robotics. It's an off-road robot. So this can go on like soil and stuff like that. We used to try this in a grassy patch of land, and I think it was meant for a farm use case, but we never got there. At least not in the 1 year that I was there. And the other one, this one here, it's a Segway essentially, and it's self-balancing. Actually, no, this one's not. Sorry, there is a wheel in the back. It's a small wheel in the back, which prevents it from falling over. But yeah, this was meant for like indoor deliveries, so you could send stuff to another colleague in another building or in another room. And this right now is ferrying lunch from a cafeteria to our cubicle, because yeah, just like that, for no reason. Yeah, so I realized when I was making this presentation that there's not much publicly available videos from our robotics team at NVIDIA. So I don't know what happened to that. My current gig is at Plus AI. So we are in California, in Cupertino, in California, and this company got established in 2017. I was like number 10 employee, and we are an L4 self-driving truck company. So these are our trucks. The picture on the top right. So that's what we haul. All the brains sit here somewhere, and this truck is hauling 18 wheels of 18 wheels. It's a full Class A truck, and we recently completed a freight load carrying butter for this company called Land of Lakes. I guess you must have seen their butters in grocery stores. Yeah, we can watch this video. The background score is pretty good too. So this truck is, this is where obstacle detection comes in, object detection comes in. So this truck detects objects, this truck detects lanes, this truck detects traffic lights, other cars to not hit, toll booths. We also do a lot of planning, and of course controls. It's a drive-by-wire. I guess some of you might be aware of that term. So basically, you send. Yep, go ahead.
Oh, sorry, I just had a question.
Yes.
Earlier on the slide, it said this is level 4 autonomy. What does that mean?
So there's in the self-driving field, there's different levels of autonomy as they've classified them. L1 being you are driving your car. L2 is driver assistant systems. So right now there are features in a car which brake automatically, or which prevent you from drifting off into another lane. So forward collision warning and lane departure warning and stuff like that. Those are called L2 systems. People have conveniently skipped L3 because there is no clear definition for L3. L4 is a system where you are in the vehicle, but the system is doing most things. So like this truck will drive itself for like 99% of the times. 1% of the time, the driver might need to take over. So you don't have to keep your hands on the steering. L5, which is the highest level of autonomy, means there's no steering wheel in the vehicle. And you just tell the vehicle that, hey, you know what, I want to go from point A to point B, and the vehicle or the car just drives itself. It figures out the route, it figures out how to navigate, it figures out just driving there. There's no need for a steering steering in the vehicle. And I think we're a few years far from there, but Tesla tries to do a lot of L4, L5. Our trucks are L4 capable. There's a bunch of other companies which are doing L4/L5. Yep. So those are the levels.
So I have a question on like, I guess how commercially available, or like when it will become commercially available. So I know like a lot of this stuff is obviously still under testing and all that, but if you were to give an estimate for like how long you'd start seeing these, or how long until you start seeing these on the road, what would that be?
That's a hard question, man. It's there's too many things around it. There's one part is the tech, and the other part is the governance. Our governments and the regulations have not caught up with the industry. So even in the US right now, all states don't agree with the expectations and capabilities of L4 and L5 systems. So it's a really hard question to answer. In terms of tech, I don't know, 5 years, 10 years, it's really hard to say. And I think since you all work with robotics and sort of are interested in STEM, you guys will appreciate this problem that more often than not, most of the times, 99% of the time, your stuff will work. Like the code that you write, the designs that you create, the systems that you make. That 1%, when it fails, is the one that hurts the most. And you can imagine this is a truck. So for the 1% where it fails, it could be catastrophically damaging.
So what are some of the failures that you would see in experiments with autonomous vehicles?
Oh, tons of types. And more often than not, it's not even our truck. It's other people acting stupid. So we have this term called idiot driver in our error logs. Like whenever we see something stupid happening on the road, we tag that as like idiot driver kind of a thing. So people have actually swerved into our lane because they fell asleep on the steering. One time someone went over the railing and then swerved back into the railing because they'd fallen asleep. So these are those 1% of times that your system does not see a lot. So I, as a programmer, cannot write code to bypass those problems. So at worst, your truck comes to a stop. But then if a vehicle is parked in front of it and there's casualties, what is your truck gonna do? And once, I think we also had a plastic bag cover one of our cameras. And I thought that was very funny. Like you actually need to have a person go up to the truck and then remove that plastic bag so that the truck can start working again.
So is there a way of knowing, like, is there a way for the robot to know itself, like there is something obstructing its view, or does it just think that that's what the road looks like?
No, so we have those smarts built in, like it's all algorithms finally. Like if your robot keeps seeing this blank screen for some time, then your algorithm is supposed to say that, oh, you know what? This information does not agree with information I'm receiving from other sensors. Usually in these robots, you don't have just one sensor. We don't have one camera. We have like 7 cameras and more than 1 LiDAR and 5 radars. So information from all of these sensors has to agree with each other. So if one camera gets covered, the system, the smarts that are built in, they say that, oh, you know what, this one camera says that nothing is changing in the scene, but these other 6 cameras say that there's a lot of rapid movement in the scene. So definitely this one camera is bad. It's called sensor fusion, where you take multiple types of sensors or even multiple numbers of sensors and sort of correlate their information. So yeah, so we completely know when that camera goes down, when it's covered in something, but then a person needs to go there and clean that up, right? Because like, if you imagine from a robotics point of view, like a plastic bag removal assembly is a project in itself.
We've also got 2 questions from the chat, if you don't mind.
Sure.
One's asking if the Snapdragon processor is commercially available.
So last I checked it was, but I think that project keeps changing its specs. So I do not know. But right now, I think Qualcomm has an offering from the robotics department. And if you guys are interested, I can send you guys some links.
And a question is asking, how long will it take for Snap AI to reach level 5 autonomy?
So I do not know what Snap AI is. Our company is called Plus AI.
Oh, I think that's what they meant.
Okay, but if that's what they meant, then it's a hard question, as we were just talking about. It's hard to answer because it's not just the technology. It's also a bunch of government regulations, and you have to make sure that trucking agencies conform to these rules, and what happens to truck drivers. How do freight companies deal with these things? So yeah, there's a lot of testing. We have all the tech. This is a huge integration and testing task now.
All right, so yeah, that's all for questions for now.
Okay, there was, I think, one question. What would be the application of the drone robot be? All right, so there's multiple applications. One application that I was working on was home security. So let's say you have a security alarm sort of thing built into your house. There's a bunch of companies that do that, right? I forgot the name, AD&T and all these people. Yeah. So imagine that one of your home alarm systems says that your rear door is open, or your rear door just opened, and you are outside of your house and you don't know what's happening, and you don't have a camera in that thing. So there's like a blind spot on camera or something. So instead of like covering your house with cameras, which just seems like a weird privacy violation, you have this robot which takes off and like goes to that location, circles around, gives you a very good view of, hey, what's happening, what's not happening. Like, was the door opened? Is this a bird, an animal, a person, a thief? And then just reports back to the system. So surveillance is one thing, and then you can do a lot with the law enforcement, fire. So if there's like smoke in a house or fire in a house, you can send these robots out, and then they can map the area, get a very quick view of what's happening, so that you don't have to like send humans inside there. There's also other use cases, like Amazon is trying to do drone delivery. Not just Amazon, there's a bunch of companies which are trying to do drone deliveries. So that's a pretty cool use case too. We actually delivered I forgot. Slurpee, yeah. We delivered a Slurpee in Las Vegas. I do not know which company it was for, but yeah, we flew a Slurpee from one person to another person in the desert of Vegas. So that was cool.
So I guess this technology can like help not just restaurants, but like any company deliver products outside of their normal reach, right? Because drones have that capability.
Oh yeah. I think there's also one I remember. There's a startup which was doing like they were sending defibrillators through drones. So if someone has a heart attack and there's a defib not like easily available, so this drone just like zips, lands next to that person, and anyone can like use their defib on them. So that was cool. I think there's also drones doing medicine and vaccine delivery in Africa, which was also pretty cool. Oh, which reminds me, there's also like anti-poaching with drones. So instead of people like patrolling areas, you can have drones flying around and keeping an eye on like herds that you need to protect.
So could these, or do we know what the carrying capacity on average for these drones is? Like, what's the maximum weight they could lift, I guess?
So drones have this thing called weight to thrust ratios. It depends on the size of the drone and how it's built, the batteries and everything. I do not know a whole lot about it. I depend on the hardware team to tell me that. But it's a field that has been studied very well, and you'll find a lot of material online. It also increases. Actually, sorry, I do not know if it's proportional to the number of propellers you have, but I think there is some formula to calculate that. So if you have a quadcopter versus hex versus octocopter, I think you can lift more weight, but you spend more energy. So you could lift more weight for a short amount of time. There's a bunch of calculation around that. Apparently, helicopters are supposed to be most efficient because there's only two blades. But yeah, they're also harder to control.
So final question, I guess. If the what's the word I'm looking for? Like, are the quadcopters designed for like specific products to be carried out, or does like if you change whatever it's carrying, would that affect how it balances itself out? I guess like what I'm asking is, can the weight change of what it carries?
Yes, up to a certain degree. It again sort of ties back into the weight to thrust ratio. So let's take an example of a drone that's flying. It needs to fly carrying some weight. That means it needs to generate some thrust. That means the propellers need to spin at a certain rate. If you increase the weight that it's carrying, the propellers will, you could spin the propellers faster and it will generate lift. But since you are expending more energy, over time, it's not going to be able to generate that much lift. That means whenever you're maneuvering that quadcopter, it's going to be affected. And there's also things like, sorry, let me rephrase that. The size of the weight or the shape of the weight that you're carrying. So if you change the center of gravity a lot, then your controller needs to be reprogrammed. So the thing that's moving the quadcopter, so roll, pitch, yaw, it needs to be reprogrammed to say that, you know what, my center of mass is this much now, or my center of mass lies here. So I need to do that, do this, do that. So in I guess to summarize, depending on what you're carrying, like if you have a sort of flat cuboidal package with a certain weight range, I think your drone can pick that up. But if your package is changing shape drastically, then you might need to reconfigure your controller. It does not affect perception as such, but it will affect the controller. It's very similar to how you drive, let's say a coupe versus an SUV versus a truck which is hauling a boat. You as a driver do not change your rules of the road, but you become more, the way you control your vehicle changes. You can't be as aggressive with a truck hauling a boat as you can be with a small car. Does that answer your question?
Yeah, a little bit.
Okay. Right. Okay, so now I'm thinking that I should have probably started off with this slide. Anyways, so what is an autonomous robot? The word autonomy is derived from, it has Greek roots. So auto is self and nomos is custom or law. So essentially self-governing or working under a law of the self. So an autonomous robot has the ability to make decisions in a defined space or environment or for a particular use case. Robots are usually expected to be autonomous for like specific use cases. So something like Terminator is an autonomous robot, of course, but it's sort of far from our current standards. A human is an autonomous robot because they can do a lot of general things, but robots that we build are usually meant for one or two or very limited use cases, and we expect them to behave autonomously in those. So here I got some cool examples of autonomous robots that are used in today's world, and let's look at those, and then yeah, we can just like talk about them. Before we go, any other questions? right? Cool. So this is one of the coolest robots in today's world right now by Boston Dynamics. I guess a lot of you must have seen this one. It was a huge rage when it was announced. So this is called Spot. It's a dog-like robot from Boston Dynamics. So this robot has a bunch of sensors built in. It can navigate these weird like terrains, go over them. Avoid other robots. And you can also like add attachments to interact with real world objects. Oops. My bad. All right, so someone had a question about payloads, right? For quadcopters?
Yeah.
Yeah, okay. So this is not a quadcopter, but so this can give you some sort of understanding, or maybe I can explain better with this example. You see that cinder block that the other robot in the background is carrying?
Yeah.
So the Boston Robotics Spot, it's this amazing robot, and this team is really good at controls. So what they do is you can place this heavy object anywhere on the robot, and the robot can figure out how to balance. So if you put it in the center, all the legs will bear the weight proportionally. But if you put it too much on one side, it can actually figure out how much it has to list, and the other legs will compensate.
So the robot basically knows its own weight, and it's able to adjust for any, I guess, irregularities.
Yeah. So there's again bunch of sensors built everywhere. So there's sensors at each joint. So each joint knows the stress that it is feeling, and then compares it with other joints. And then it can figure out, oh, you know what? I need to be in this state to be stable. Similar to how there's, I think, vector torque routing in some SUVs and stuff like that. It's all if you can measure it, you can improve it. So if this robot did not have any sensors, it would have no idea that, oh, you know what, I'm listing to this side, or I need to be balanced, or I'm disbalanced. But just because you have tons of sensors built in, it can do those things. Same for quadcopters. You can have there's actually the quadcopter motors have some sensors which tell you how much electric current they're consuming. So if your robot is actually, if your quadcopter is swaying to one side, the current being used by each motor is different, and then you can do something on top of that. There's like a whole list of algorithms. It's not a very simple thing, but it's like a field that controls people study a lot, controls and control systems. Does that help answer your question slightly better?
Yeah.
Okay.
Also, like, so what are some of the sacrifices that are made? Because obviously a drone can't have all of the sensors that Spot or some of other, I guess, land-borne robots would have. So what like sensors do like you get rid of, I guess?
Yeah, so we'll talk about that, but mostly what I've seen on quadcopters, you end up only using cameras and IMUs, of course. IMUs are sort of integral to everything. Every chip nowadays comes with an IMU in it. Every robotics chip, sorry. So IMU and cameras, because they're light and they don't consume too much power. I have very rarely seen a quadcopter with a lidar or with a lidar mounted on it. Yeah, I have seen one, but it's very rare. It's only for research mostly. There are some really large quadcopters, usually used by agriculture farms, and they're huge. They're like, the wingspan is as big as like a human. So those can lift a lot of weight because they also need to lift manure and fertilizers and stuff like that. So there, a lidar is actually weighs much less than your payload. But depending on your use case, if you had a quadcopter which had to fly indoors, you would not put a LiDAR on that. There's like literally no way that it can lift that. Okay, that's good. This is another really cool one, which is used a lot, and I'm sure all of you guys use Amazon. So this is an Amazon fulfillment center, and yeah, these robots actually do the bulk of the stuff. So they move shelves around. You'll see these markers on the floor. So these robots actually read these markers, go on top of them, and then figure out where they need to go. So they are autonomous in that sense. They move these whole shelves around, and then another person or another machine can pick stuff out from this shelf, put them in a box, and then that's what gets shipped to you. And these warehouse robots are actually very common now. Almost all big warehouses use them. It's like places in China, India, Singapore. So these ones, I don't think they have a LiDAR. They have a camera on the bottoms for this to detect this tag on the floor. And I think they also have some sort of camera or proximity sensors on the sides, so they can avoid colliding with other robots. But here you see, yeah, these robots are bringing these shelves. This person's like picking up stuff from these shelves depending on the order that was placed. Here's one robot which uses a vacuum hand to pick stuff. This one, vacuum? Oh no, this one's not vacuum. Sorry. There's another one. There's another video where it uses a vacuum, I think. Yeah, this one's like a forklift. There's another cool one, which is an autonomous robot in a field. Oops. Okay. So yeah, so this robot just drives around the field, looking for bunches of grapes that can be picked. And I think right now they're doing a data collection run. Yep. So this robot uses GPS, cameras, lidars to like create a map of the surrounding that it needs to move around in, and then it can autonomously go to a specific place, pick some specific things. So these robots are actually becoming, at least the research is becoming really common nowadays. So you can identify like different pests in a farm, or different diseases on plants long before like a human can. So they scan an area every day. Yeah, so this here is a LiDAR. And looks like they also have cameras here. Yeah, so this is like scanning this area. Yep. It creates a 3D model of the stuff that it's seeing so that people can analyze it later on, or you can over time do some analysis on that data. Like how fast is the plant growing? Is it rotting? Are there grapes on the plant already? Cool. Automatic dispenser deployment. I don't know what that means. All right. So this one, this is another autonomous robot, and it claims precise movement, and that's usually because of sensors mounted like this. So you can see, I think there's some cameras here, or there's cameras here. So instead of blindly saying I'm going to put a box here, it sort of tracks that box and adjusts its position accordingly. And that's all perception and computer vision. This is similar to the Amazon warehouse stuff that we saw. Here's another cool one. So that screen is how the robot's probably seeing things. So it's looking at this. There's a camera probably somewhere on the arm. Actually, probably not the arm, above the arm. And it's looking at this screen or looking at this image and saying, oh, you know what? This looks like a raw burger. I'm going to flip that patty. And I think it has some timer sort of for each burger that it has placed. And it's going to flip that burger after some time. Yep, it says flip on 80 seconds, 68 seconds. Yeah, this is the screen that's probably shown to a human so that they know that the robot's not doing anything funky. Mm. Yeah, so that sensor is probably placed at the second, at somewhere on the second joint right here. And it cleans the grill too, so that's nice. I have a question for you guys. What do you think about this? Would you say that this is an autonomous robot?
I guess it's just like one really spread out autonomous robot.
So I don't think this is an autonomous robot because it's just a conveyor belt with bagels on it, and there's like people watching that, ready to flip a switch if something goes wrong. Right here. So it's like, imagine if something happened, if these people were not there and maybe there was a bagel mishap, then this area, I think, would just be flooded with bagels.
Oh, so there's like no sensors, I guess. Is that
Yeah,
what's
yeah.
Okay.
Yeah, yeah. All right. So we looked at some videos of autonomous robots out in the real world. Now, what does it mean for a robot to be autonomous? So there's three things that a robot needs to be doing for it to be autonomous. It needs to understand the world around it, which is seeing or perception. It needs to figure out what to do now, so decision making or planning. And then it needs to interact with the world, so actuation or control. And this is really very similar to how we as humans behave. Like if I want to pick up this bottle of water, I first need to figure out where that bottle is, or actually understand my world around me and say that, you know what, there's a bottle of water which is lying on a table next to me. I need to figure out how to hold that bottle. So like where to clamp my hands around it, and then actually take my hand towards the bottle, clamp around the bottle, and then actually do that stuff. So these are three things that a robots need to do, that a robot needs to do. And how do you make a robot autonomous? So there's hardware, which is sensors, all the computation and processing power. So all the, the processing units that we talked about. For example, the Snapdragon thingy. And software to drive this hardware and then consume this information. And of course, the blood, sweat, and tears of the people that are working on the system. Right, so where does, and I majorly work with the first field, which is understanding the world around the robot. So that's what I'm gonna talk a little bit about today. Perception, so humans perceive the world with these senses. I'm sure all of you have heard of sight, smell, hearing, touch, and taste. There's also two more, which is proprioception and equilibrioception. And proprioception is one of my favorite ones, which is at any point of time, a regular human being has a very accurate sense of where their limbs are. Like right now, my hand is at some distance from my face. I did not even have to look at my hands. I just have a very good model of where my limbs are, where my legs are, where my hands are. And it's actually pretty freaky when you think about it. That your body can do what it does. So these sensors are what enable us to do things. Like when I'm lifting my bottle of water right here, I'm not like looking at it. I'm not making micro adjustments by looking at that bottle. My hand just reaches out. My brain has a model of how my hands work, and my brain has a model of where my hands are, and just like commands it, which I think is really cool. If there were a sensor like that in robotics, that would be so awesome. But anyways, robots or autonomous systems need something similar. They need sensors. So some common sensor for perception in robots, for seeing the world around you, there's cameras, LiDARs, stereo or depth cameras, radars, and ultrasound, infrared, proximity sensors. I clubbed them together sort of because they usually serve the same purposes, at least for the robots that I have worked with. And of course, there could be more in the world. There's people are coming up with the cool sensor integrations and configurations all the time. And then sensing your position in the world, which is GPS and motion capture systems. So let's just start from the top. I'm sure all of you are aware of cameras. This image on the bottom right, that's the data from a LiDAR. So LiDAR stands for light detection and ranging, or laser detection and ranging. Actually, I think it's light, yeah. It sends out a laser beam, and then this beam gets reflected back, and your sensor then tells you that, oh, you know what, I sense an object at that distance away at that point. So it gives you 3D information, while a camera only gives you 2D information, just tells you that there is a pixel at that location. This image on the top right is how a stereo or a depth camera looks. So basically at each frame, it's derived from cameras, and at each frame, it gives you some estimation of where an object is. Like here, you'll see these yellow to purple colors, yellow being really close and purple, dark purple being the farthest. So the bottom row is what your camera sees. So your camera, or you as the programmer, can make inferences that, you know what, I see this object really close to me. I see some objects really far away. I see this gradation of things. This could be an area that I drive on. Then there's like, I don't have a picture for radar. Why do I not have a picture for radar? I think I accidentally deleted that. Sorry, guys. So radars are sort of similar. They're sort of midway between these two. And then sensing your position in the world, there's GPS. When you drive around in a car, when you use a phone, you have GPS. So it uses a system of satellites to tell you where you are located in the world. This system does not work on its own. Like if all the satellites of the world were to go off tomorrow, your GPS would be rendered useless. Same for something like a motion capture system. A motion capture system is basically an expensive system that has a bunch of cameras. Yep, right here. So you see these cameras. These cameras are tracking objects in their field of view. So you set up this rig system, which is looking at objects and telling you where this object is. So the sensors on the top, sensing the world around you, they are ego sensors. So basically, they depend only on the object. So I am carrying a camera, and that's it. That's all I see through. The camera only knows the world through its own eyes. It has no other external reference. Same for the other cameras listed here. But sensing your position in the world, these two sensors, GPS and motion capture, they have a view of the world, and they tell you where you are in that world. So these are two important sensor types that mostly are used in robotics. So I'm assuming you guys also. So you guys talked about cameras. So you definitely use cameras.
Yeah, so from what I'm seeing, like listed on the sensors, I think cameras are the main ones that we use. You mentioned an IMU earlier. I think that's also something that
Yeah.
some of us are somewhat familiar with, but yeah.
Okay. Yeah, I didn't want to list IMU because the thing is, IMU and perception is a slightly complicated domain. It usually ties into this thing called visual inertial odometry. So vision and inertial odometry. So, but that's a very interesting topic. All right. So, given these sensors, the perception tasks that are relevant to autonomous robots are these two tasks. I think everything can be grouped into these two. So, what am I seeing, and where am I? And if you can answer these two things with your perception module, then you can enable both your planning and control. Because each of these robots that we looked at, if that's the question that the perception system is answering. So when Spot is avoiding another spot or avoiding another object, it's looking at what am I seeing, and when it's able to navigate, it's thinking, where am I? So this is a good example of motion capture. So OptiTrack is a company that makes motion capture systems, and this is one of their videos. This was made with Lexus. Yeah, so these quadcopters right now, they're flying around. They are tracked by these. You see these cameras here on the top, this square-like thing, and then this keyboardal thing right here. So these are motion capture cameras, and these quadcopters have small beads, retroreflective beads on them, and which track their position at every instant of time. So the very first video of the quadcopters that I showed you, that the quadcopter was doing its own thing. It had no motion capture system. It was just flying on its own because there were some computer vision based smarts built in. These robots are dumb that way. It's like there's no processing on this robot. The processing is happening in terms of controls. So there's a controller which is controlling how much each propeller is spinning, but there's not much else going on. All the information is coming from an external system. Oops. So that's what a motion capture system does.
So I have a question. Like, you've been in the industry for I think almost 10 years now. So what has changed like the most drastically, or what's improved the most in terms of hardware or software?
I think deep learning was the biggest game changer that I have seen. So sensors have not changed a lot. Actually, hardware has not really changed a lot other than compute. So computation powers get better every year. That's fine. That's known. But deep learning that way has changed things a lot. You can do a lot more things lot more things have become easier. So all of these people you're seeing right now, I used to work with them because Qualcomm acquired this company, and they're all experts at controls. And they have like PhDs and they worked on their control systems for at least 15 years. And it's all mathematical. But with deep learning now, you can collect so much data and you can actually build a model without all this know-how. So it's become really democratized and easier to build systems. And also we'll show some examples of deep learning in some coming slides. So yeah, I think that's what has changed. The sensors have not changed, the hardware has not changed, the way we are using them has changed, the algorithms have changed. Does that answer your question?
Yeah.
Okay. So on top right is another, is this thing called fiducial markers. Do any of you know what fiducial markers are or what this marker is? This thing right here. Cool. So you should check out that link under that image. This is a really well-known fiducial marker in computer vision. So basically you print out these things and then you stick them around and your camera, and you use this library, and your camera helps you understand where it is. Each of these markers has a specific pattern and has a specific shape. So by reconciling all that information, you can actually figure out how far your camera is from this marker and where it's looking and how it's oriented. So let's say you are to pick up a block of like a block, and you paste this marker on that block, and you're in like really few lines of code, you can actually enable your camera to see where that block is located. And then your planning or control module can figure out how to move towards that block. So I think that is a really cool example. This is a sort of old library, like it's been used at least for 10 years for sure. I have used it for most of my graduate school projects. Sorry. Right. So I talked about perception. Perception sort of has these, all of these tasks are sort of interrelated, but perception is like this umbrella task, which also covers computer vision and deep learning. So computer vision, it's if the computer is the brain, then sensors are its eyes. And computer vision is this art and science of enabling human-like vision for machines. So just like what we do with eyes, computer vision allows you to do that for machines with cameras. And most commonly used sensors for computer vision are cameras and lidars, because both of them use the visible range of light. So some robotics use cases are object detection, which you guys already do. Then there's object tracking, which is a step built on top of detection. And then understanding object motion. So how are things moving around me? And then there's some other really cool applications, not in robotics, but there's AR, VR, computer graphics, and CGI. All the CGI movies that you guys see is a product of computer vision. Holograms are computer vision. There's like also some other stuff like face morphing, animojis. All of that is like derived from computer vision. So I'll go through these videos. My laptop does not allow me to do full screen anymore. Right, so in this example, we are using a camera mounted somewhere, and it's looking at these this traffic on a freeway. And without any information about what a truck is or if there is a bounding box around a truck or not, it's not detecting any objects. It's only looking at two frames and then figuring out how things are moving in those two frames. So this is a really cool example, and it's a really simple algorithm that is used a lot in robotics. What's going on? Sorry guys, give me 1 second. Yeah. So it's just, this is called optical flow. And do you guys use this right now? or is anyone aware of it? Okay, so this is actually really simple to use, and it's available in like open source libraries like OpenCV. And so let's say you're tracking a ball going by, then you can use something like this, and it drastically improves tracking quite a lot. So you just take 2 image frames and then look at the differences between these 2 frames, and then figure out how things are moving. And this is a really fast algorithm. You can run it at like faster than a camera frame rate. So you can run it like 3000 FPS or something.
Yeah, I think
Sorry,
we do,
300 FPS.
yeah, I think we do use the OpenCV library for vision. But yeah, I just don't think we know like how it's constructed or how to deconstruct it. So yeah, this is pretty cool.
Yeah, this is like my go-to algorithm whenever I have a tracking task. And actually for the trucking space that I work with, or self-driving space, it's actually fairly useful. Like you can track objects. It even shows you interesting features in the image space. Then you also have some color-based tracking and detection and tracking. So this code is just using color. It's detecting a green ball, a red ball, and a blue ball purely by color, and it's tracking those. So again, it's really fast. You don't need any deep learning. You don't need any special models to do that. So I don't know what your robotic use cases are, but this seems like a very like a first robotics kind of a thing where you have to detect a specific color of an object and pick it up. One of my grad school projects was picking up Lego blocks, and we used something similar.
How quickly is this vision pattern able to like detect objects and track them?
Usually it's super quick. It can do it as quickly as you can send images. This is a really fast algorithm. It has to do nothing. It just parses over image pixels and makes a decision. So I'm assuming you guys use camera images at like 30 FPS, no more than that.
Yeah, probably around the 24 to 30 FPS range.
Yeah. So this is perfectly fine for that. And OpenCV also has built-in like, so filtering by color is fine, but it also has like contour detectors and connected component detectors, and you can estimate shapes, and you can filter circles from other shapes. And that's like really fast. So that's why object detection and tracking together work really well. So if you were detecting an object in every frame, that's kind of expensive. But once you detect an object, you can make some inference about it and only track in like a small area around it. So that makes things really fast. This is a more involved example, but I think there was a question about this in the beginning. I forgot what the question was, but this is the camera understanding the space that it is around. The camera is only seeing this image, but from that image we can pick out specific parts of the image which are interesting to us, and then generate maps out of those. I know I'm butchering the explanation right now because it's not something that you can explain in a few seconds. But SLAM is called simultaneous localization and mapping, and it's an awesome study. But yeah, it's a very advanced field also. But yeah, it essentially takes a bunch of image frames and then spits out a map for you to work with. So if you keep watching this video, this person is looking at, or this camera is looking at these frames, and it will generate a map because it's looking at these specific features. Yep, so it created this map that it's now driving in. It's all accumulation of information from one frame to the next. This is sort of slow though. I mean, you need a lot more compute to do this for 30 frames. And for most object detection cases, you probably don't need it. if you're building a robot that needs to navigate in free space, then yeah, you need something like this. Then you need localization and mapping. So those greens and the blues are the path that the camera was taking. The white is the map that it generated. And then here, that shift doesn't seem to be working, but here's an example of AR, VR, and that's also computer vision. So basically someone pointed their camera at a hand and you can place this robot on the palm of the hand. And this is again computer vision. So you track the palm, you create a surface on top of that and plot this object. What are some things that you guys do for robotics? Like what are things that you guys are interested in?
So I can't speak for this year too much, but I know that last year's challenge was heavily dependent on computer vision and motion profiling. So being in robotics, I guess kind of brought a natural interest to those two fields.
Cool. So we talked about computer vision, and then now it's deep learning. So it's the state of the art for machine learning and pattern recognition. So this field has made drastic improvements to classical computer vision, what we saw in the previous slide. So from something being really algorithm heavy, we have come to data-driven applications. So you collect tons of data, you label tons of data, and then you have these deep learning models that you can train. And then these models are essentially, these models become your algorithms. So for example, this GIF on the top, which shows a bunch of objects being detected. So there's like people, there's cars, there's poles, traffic lights. There's a truck in purple. So classically, if you had to do this, this is a really hard problem. So before 2011, people did really poorly on these things. And since 2011, when deep learning became very mainstream, yeah, it's everywhere. We use deep learning for almost all object detection tasks. Under that is human pose estimation. So there's like off-the-shelf models which you can use where you can detect every joint in the human body. There's this the image on the top right, which talks about. Oops. Yeah, so this is called art transfer essentially, or artistic style transfer. So you have this random image, and then you have all these really okay. So these pre-existing styles from different artists, and then you can actually convert this image into any of these styles. So this again, someone trained a network with a bunch of data, and then this network learns that, hey, when I get an image, I transform it into this style. So this does not apply to robotics, but it's a pretty cool application of deep learning. Here's an example of a robot learning how to pick using deep learning. So in this case, I think they use a camera and some sensor to tell them if they were able to grasp onto an object or not. And then over the course of time, this model that then learns how to grasp things. So you can imagine that if you, as a person working with this robot, would have to like look at perception tasks, would have to look at controls, planning. But in this case, this is like an end-to-end model which does everything. It just needs a lot more data to train and a lot more data to learn. So you can imagine leaving this robot running like for days, and then it just learns. but it's a special family of algorithms. It's not a simple family of algorithms. And then on top of that, there's another cool thing. But yeah, so NVIDIA had done some work where they created a simulator where you could simulate like thousands of robots. And then instead of training one robot, you train thousands of robots in simulation. So now you have all these robots trying to learn how to run, and then they learn from like thousands of different experiences, and then like they can really quickly figure out how to learn, how to run, how to do parkour, how to like climb over steps, how to navigate all this weird terrain. So this, I think, is also a very significant step that we could not have done a few years back. So now we have improved simulation softwares, and GPUs keep getting better and better. So for something that would have taken months to do earlier, now you can actually create simulation environments pretty easily. So you can do that very, very fast now. You can simulate multiple experiences for your robot. So something like deep learning is usually an overkill if you're doing something simple. So for example, this thing that I showed you, color-based detection and tracking, or this optical flow, this is really awesomely done with classical computer vision. It's a super simple algorithm. It's super fast. But to do that with deep learning would be an overkill because you would need to collect so much data, and then you would need to train your models and blah, blah, blah. And it's also very compute intensive. Deep learning needs a GPU or at least some dedicated processing unit or compute unit to do your inference. But it's extremely strong if you have a very large amount of data or a very large problem space. So for example, since I work with self-driving trucks, we see different types of cars, we see different types of pedestrians, we see different types of trucks, and like different colors of cars, different shapes. So it's really hard to create a model for each of those. So then it makes sense to like collect and accumulate data over the years that you're driving on, and then figure out models that can infer on top of that. So for something like that, deep learning is awesome. And there's also a myriad of open source implementations available for deep learning. So even if you are a beginner, you don't really need to do stuff from scratch. Things are super democratized now, and you should be able to use a lot of these things very easily by yourself. If you guys want to talk a little bit more about computer vision and deep learning, I can always like come back and we can talk about specific problems. Okay, so this is the sort of the end of like computer vision and deep learning stuff that I want to talk about. Are there any questions before I move on? Cool. So now that you've talked about that, so here are some small tips from someone who works with robotics. So define your problem. Albert Einstein has a saying that if he had an hour to solve a problem, he'd spend 55 minutes thinking about the problem and then 5 minutes implementing solutions. And you should do the same thing for robotics. Don't just go out and build something. Whatever you're building or whatever you're trying to solve, spend time thinking about it, and then constrain your problem. So you could be constrained by size, shape, power, cost. There could be so many other things. Just keep those in mind before you start choosing sensors and algorithms to work with. And then break the problem down. So split the problem into tractable, coherent chunks. Perception, planning, and control, as you talked about, like the three things that make a robot autonomous, they can usually be separated and worked on in parallel. You don't need one continuous pipeline to work at the same time. And then you can do integration tests and figure out how they're working together. But you more often than not, you don't need to work on all of them at the same time. And then since you're breaking these problems down, you should communicate expectations and requirements from one module to the other. Now this helps you design like small modules which can be plugged in. And this makes things very easy because if you're trying something else out, you can just like swap something for the other. So you understand and design requirements around each module and then what it expects from each other, or what they expect from each other. So you can work on things in parallel. So like, for example, let's say you're tracking a ball. The perception module can say that, you know what, I'm receiving data at 30 FPS, and I will give you data output at 30 FPS, and my data is going to look like so and so. So I'm going to tell you the pixel location of the ball. And then planning module will be like, okay, you know what, I'll convert this pixel information into some other world space, and then we can act on control on top of that. So as long as you have these requirements and these expectations set in stone, sort of, each module can work independently. So one person does not need to deal with perception through planning. And then simulate if possible. So hardware is hard and time consuming. It's also slow to collect data, but of course it's important, but it's hard and time consuming when you have to do it all the time. So if it's possible, use simulations, use your pre-collected data. If you're working on perception algorithms or perception problems, collect some data and then just iterate on top of that. Test each module often. You don't want to like just be developing and then not testing. That's usually a bad idea. And then do integration tests regularly. So if you're working on perception and planning separately, just make sure that occasionally once in 2 weeks, sort of, like they're working fine. Once in a week, they're working fine with each other. You can't outrun a bad sensor. If you have a valid use case, or if you have a use case that you know you're working on, try to use an appropriate sensor. If you have a sensor that needs depth information, it probably makes sense for you to use a stereo or a depth camera. Like, don't try to cheap your way out by using a camera and then having crappy information. A good sensor and a good configuration will save you a lot of time and effort in future. Again, this is sort of limited by your cost. Maybe you're limited by how much money you can spend on the sensor, but usually this is a good idea. Use a good sensor. Don't cheap out on sensors. And then this is a pretty common rule of thumb. Just keep it simple, stupid. So always opt for the easier algorithm or the approach, and because they're always easier to use and tune, hack, and test. Something that is really complicated is always is usually also hard to work with. Like, you might get it to work for one case, but it may not carry over for other cases. And build on the shoulders of giants. Don't reinvent the wheel. If code exists to do something, you probably don't need to rewrite your own thing. Any questions? So sort of adding on for the perception problem, all those things that we talked about apply. And then again, for the perception problem, spend some time thinking about what you need to see and what you need to understand. Like, what is the minimal thing that your robot can get away with? Because all these things that you are doing will be compute heavy. Anything that you add on to your algorithm will take away or eat away into your computation power or your time. How often do your modules that are using perception output need to use that output? So for example, if you're making a ball catching robot, that would need to be significantly high rate input compared to a warehouse robot where things are mostly static. Because if you're catching a ball, then you need to move a lot faster than a robot which is just like rolling on the ground. So what sensors you should use? So this is all listed in order of cost and some sort of general use cases. So there's like proximity sensors, which are really cheap, but you need to have a very clear or a very specific event that you need to detect. And there's cameras, which are useful for object or person detection, tracking, and they're really good for marker-based environments. So the APRIL tag thing that I talked about, if you can use those, then camera is awesome. You don't need a whole lot of localization and understanding of the world that is built in. Depth cameras or stereo cameras are awesome when you need a distance estimate, which a camera is really poor at giving. They could be sort of more expensive than cameras, but they're not prohibitively expensive. LiDARs, on the other hand, they can get super expensive. They give you a very large field of the view, so they're very good for getting like the lay of the land, so you understand the whole world around you. But they're usually more expensive, unless your lab has some or something. GPS is awesome, but since I think you guys mostly do indoor robots, right?
Most of our robotics is all like exercise indoors.
Yeah, so it's probably not very useful for you guys. Motion capture, I am pretty sure that you guys are not even allowed to use motion capture. It's also super accurate, but super expensive. And then how, depending on how you're choosing, depending on what you want to use, computer vision, deep learning, and a mix of both. That depends on how much data you have available, what computation power do you have. Are you running it on a Raspberry Pi or a laptop running on the cloud? So there's like a bunch of considerations. Think about those things before you jump into an algorithm. And stuff nowadays is like very democratized, so it's really easy to use things. And you don't have to be like married to a set of sensors or some compute library or some computation platform. I think robotics is getting a lot more easier and a lot more fun nowadays. All right, guys, that's the end. Up for questions.
So what initially sparked interest for you in AI and machine learning? Oh, and I guess now computer vision.
So I always started with computer vision. Even in my undergrad, I was doing a lot of image processing and computer vision. And I came for my master's wanting to do computer vision. And then deep learning and machine learning happened. So my first interest was computer vision. And then deep learning is something that everyone now has to pick up if they're doing computer vision. And I think you asked what sparked your interest. Actually, do not know. I was always interested in cameras. I was actually always interested in electronics. And when I started my undergrad, there was this professor who was doing some really cool stuff with image processing. So I think it was it was cancer cell detection with image processing. So that was my first introduction to image processing, and that was like that's what sparked my interest.
How do you see the use of AI and machine learning and computer vision and deep learning in 20 years from now?
Good question. I feel like there's a lot of no code stuff happening nowadays. So we are going from this low level programming to this meta programming kind of a thing, where we as humans should be figuring out what needs to be done. And then these black box like models, which are using AI and machine learning and deep learning, figure out how it needs to be done. Because right now programming is a lot of how. Like you write a lot of boilerplate code, you repeat a lot of code in doing things that are happening, or doing things that a robot is doing. But I think 20 years from now, it will be a lot more meta programming. We'll have a lot more drop-in components that say that, oh, you know what, this thing does this. Let's just use that. Robotics is not very standardized right now. There is a ROS, robot operating system, which is sort of standard, but I think in 20 years, I feel like there will be something more standard and easier to use, if you will. Like it would not be a lot of boilerplate programming. It could be a lot cooler and a lot easier than it is right now. The thing that AI and ML can help with is, of course, like computer vision and deep learning is a good example of how AI and ML is helping, but also like automatic code generation, a lot of data labeling, simulation softwares. In future, let's say you want to build a grasping robot, you could just play a video game, teach this video game that this is how I want to grasp stuff, and that then teaches a machine. So there's a lot of work going on in that also. There's reinforcement learning kind of paradigms. There's also this, I forgot the name for that, but you essentially take your robot for a ride, sort of. So you hand hold your robot into doing things, and then it remembers and builds on that experience. So just like a human would teach a child, That's how I think we would be teaching robots. We wouldn't be programming them like this.
All right, so I guess if there are no more questions, we can start to wrap up. I just want to thank Mr. Agarwal for joining us today. I think we all learned a lot. I know I really did. And we'll send out an email with the link to this presentation and the feedback form if any of you want to go back to it. And we'll also be posting this entire talk on our YouTube channel in the next coming days. So keep an eye out for that. Yeah. I think, good idea.
All right, cool. Thanks, guys. Thanks for listening.
Yeah, thank you for joining us.